Everyone. This is lesson 6.3 from Algebra 1A, and technically the title of this lesson is the graph translation theorem, which you can see we're going to be talking about a theorem here. But really, big picture wise, the important thing to take away from this lesson is how to work with quadratic equations in vertex form. This is where I feel like chapter 6 really gets started in terms of talking about these things as functions. So before we dive into this too far, we need to remind ourselves that anything that has an x squared in it, or even just the original graph y equals x squared, that parent function, we talked about this back in chapter 2, these are all going to give you parabolas. So quadratics are always going to give you a graph that looks like a parabola, okay? So if we start with our old friend y equals x squared, just plain old y equals x squared, just centered right here at the origin, and we do a translation to it, and that's what this is. I don't know if you remember this notation from geometry, but this is talking about a translation going 3 to the right and 4 down. This is almost like an xy coordinate, okay? 3 to the right and 4 down. Where will the new vertex be located? Well, the vertex right now is at 0, 0. So if I translate 3 to the right and 4 down, my new vertex is going to be here, and my parabola will look like this, okay? And so the coordinates of that new vertex point, if you think about how a coordinate plane works, will be 3, -4. So really the takeaway here, because the parent function of a parabola, the vertex always starts at 0, 0, if you perform a translation, the vertex is just going to end up at whatever point is indicated by the translation. Okay, so the new vertex will just be at 3, -4. That's going to be an important thing as we kind of move forward here, because we're going to take this function here, y equals x squared, and talk about how to do a translation like we just did, and then write a new equation for it. And we have a theorem that helps us do that. This is called the graph translation theorem. Technically, the graph translation theorem works on any function, not just quadratics, but today we're just talking about quadratics. So here's the wording of the function. It says to transform a function by the translation t h comma k, replace x with x minus h and y with y minus k. Now, there's a couple of things to unpack here, but if you need to pause to write that down, you certainly may. Okay, first thing I want to point out here is the notation. We always use h and k, the letters h and k, to represent the vertex of a parabola. Okay, so anytime you see me talking about h and k in terms of quadratics, I'm talking about the vertex. Okay, this is the other part of this that gets to be a little bit strange. When we translate 3 to the right, that means inside the equation, we're going to write it as x minus 3, which seems a little backwards, right? That's supposed to be a positive 3, so why would we write it as a minus 3? This is kind of a complicated concept, and I'm going to give you just a very quick overview of it. And if you walk away from this feeling like, wait a second, I don't totally grasp that, that's okay. This is a pretty high-level algebraic concept. And you're going to see it over and over again. So you're going to get very used to this idea, and then eventually I think it'll kind of sink in. So let's suppose I have this parabola. Y equals x squared. And I take some point on that parabola. So not 0, 0, I want to use something else. So let's say I'm going to use the point 2, 4. Okay, so this coordinate here we're just going to pretend is 2, 4. And I know that's a point on this parabola because if I do 2 squared, I get 4. Now I'm going to take this parabola and translate it 5 units to the right. So I'm going to take the whole thing, I'm going to move it 5 units to the right. So now the parabola is going to be sitting here. Kind of made it too skinny there, but so there's my new parabola that's going to move 5 to the right. That means this point is also going to move 5 to the right, which puts it at 7, 4. Okay, we moved 5 to the right, so we added 5 to the x coordinate here. So when I write the equation for this pink parabola, I need it to work out where when I plug in a 7, I get 4 out as my answer for y. All right, I need this coordinate to show up on my new parabola. Well, we know y equals x squared is not going to cut it, right? If we just use the same old y equals x squared, 7 squared does not give me 4. Okay, so you may be thinking, well, we moved 5 to the right, so let's take x plus 5 and square it. Okay, the problem is if I do 7 plus 5, that gives me 12, and 12 squared is 144, not 4. I need something that's going to turn it back into a 4. But watch this. If I make this a minus 5 here, and I drop in a 7, so I put that 7 right in here for x. If I do 7 minus 5, what I'm really doing is taking this 7 and turning it back into the 2 that it used to be, right? 7 minus 5 will give you 2, and then when I square it, I get 4 back. So when we write equations for these things, equations are always going to look backwards from what's really going on. And that's on purpose. Equations have to kind of compensate. Whoops, I ran out of paper there. But equations have to kind of compensate for those translations so that the y values still come out the same, so that the input still gives the correct output. So even though we shifted 5 to the right, the equation's going to have a subtraction in it. And you're going to get used to that because we're going to do a lot of that. But I just wanted to kind of point that out up front here. Okay, so what that leads to is if I take this y equals x squared, and I take the x out and replace it with an x minus h, and I take the y out and I replace it with a y minus k, I get this equation that looks like this. Now, the only other thing I threw in here is this a value. And we're actually not going to talk about a much on this first page. We'll talk about a more on the second page, what that a value does. But our focus is on h and k, which also represent the vertex of the parabola. Okay? So this is vertex form based on the graph translation theorem, and we call it vertex form because the h and the k are just sitting there for us. Okay, and so when it's written in this form, we can look at it and say, oh, now I know what the vertex is because I can identify the translation. But a lot of the times in algebra, we like to have y by itself. We like to have our equations solved for y. So sometimes you will see this k value moved over to the other side. Okay, you'll see this k value kind of shifted, and so your equation will look like this. With the plus k on the end, okay? And that's okay. I don't care which way you write your equations. Like if I ask you to write me a formula, I don't care if you give me this version or this version, but you just have to recognize it. Like if I give you an equation like this and it's got a number hanging out on the end, recognize that that's really your k value and it belongs back over here with y. Okay, I know a lot of that sounded complicated. I think this will get easier once we go through some examples. So let's take a look at this first one. It says write an equation for the image of y equals x squared under the translation t and then 2 negative 6. Remember, when they give you the translation, what they're really giving you is the vertex. So the 2 is your h and the negative 6 is your k. And then all we are going to do is plug those values into our vertex form formula. So let me just jot down the formula here so we have it for reference. Y minus k equals a times x minus h squared. So I'm going to write y. Now, if I'm going to do minus k, and k is already a negative 6, minus a negative is going to make me put in a plus. Okay, think through that again. This is really like y minus negative 6, which turns this into a plus 6. The a value is really the number that's in front of the x squared here. In this case, there's no number in front of x squared, so I'm not going to have an a value in my equation. And then I'm going to write x minus my h value, which is 2. Okay, and that would be my equation there. Y plus 6 equals x minus 2 squared. Let's take a quick look at that. Let's see. Take a look at that on a graph so you can see the translation happen there. Sorry, this is taking a long time. I guess while I'm waiting for that to load, let's go back here. We can do this question real quick. Identify the vertex. We already did. The vertex is h and k. So the vertex here would be 2, -6. We really did that before we even did that first problem. Okay, let's see if Desmos is ready to go. There we go. Well, this is frustrating. Okay, I don't want to make you keep waiting. Let's see. We'll come back to that. We'll come back and do the graph of that one together. Let's do example 2 while we're waiting for that thing to load. Hopefully it won't keep taking so long. Example 2, identify the vertex of this function. I'm going to write vertex form up here again. And I'm going to remind you that the vertex is h, k. So when I ask you to give me the vertex, you identify what h is and you identify what k is. So the number that's in the h spot, I see a 2, but be careful here. This is supposed to be a subtraction, and I'm seeing an addition, okay? That means that this plus sign really came from like subtracting a -2, just like what happened up here with the 6. So that's really a -2 in disguise. So when you're pulling numbers back out of the equation, they flip signs, okay? Because in the equation, they're backwards from what they were originally. And then when I look at my k value, now there I do see a minus sign, and that just belongs to the function. So the k value is just 7. So my vertex would be -2, 7. This one had an a value of 4. That doesn't affect the location of the vertex. And like I said, we'll talk about what that a value does in just a minute. Are we ready? There we go. Okay, so I'm looking back at example 1 now. And I'm going to graph the original y equals x squared. And then I'm going to graph the new function that we came up with, which was y plus 6 equals x minus 2 squared. Okay, and you'll see that that function shifted 2 to the right and 6 units down, okay, which is what the question asked for, right? It said a translation t to -6. So that's telling me to move 2 to the right, which I see happening here, and 6 down. And if you click on this vertex down here, you'll notice that the vertex is right where we said it would be. It's at 2, -6, okay? Let's talk about the one that we just did. So this one, it asks us to identify the vertex of y minus 7 equals 4 times x plus 2 squared. Oh, probably can't see it. Yeah, there it is. Hiding up there. It's that blue one. Let me hide this one. Okay. And if I click on that vertex, you can see it's at -2, +7. Again, notice that those signs, the positive, negative, are backwards from what you see here in the equation, and that's on purpose. That's okay. Okay, one more example on this front side here. Write an equation for the image of y equals -3x squared under this translation. So anytime it's saying write an equation for the image, that's where you're doing vertex form. Okay, and here's my h, here's my k. So I'm going to do y minus k. Now k, it looks like, is -9. So y minus -9 is really going to be a y plus 9. My a value, I should have pointed that out. My a value is this number in front of x squared. So this is a, and I'm going to put a -3 into my function here. Again, on the next page, we'll talk about what effects that a value has on the graph. You may have some guesses already. And then x minus my h value. Now my h is also negative. H minus -1 is really going to be a +1. And that's my function. So that's really all this is taking this vertex form, plugging in the values for h and k, or taking an equation like this one and pulling the h and k values back out. That's really the important thing to know here. I'm going to continue this lesson in a second video. I'm going to split this into 2 parts just so it's not quite so long to watch all at once. So the second page of these notes will be coming up in a second video.